LLM inference, and especially fast LLM inference, is extremely important. And in this paper, we will understand how to make it faster better. So, speculative decoding. The idea behind speculative decoding is that when big model is generating next token, some of the tokens or even a lot of the tokens are actually easy to predict. Maybe there are some boilerplate routine tokens that are easy to predict. So you can use a small model to try to guess next token, and then use the big model to either accept the small model suggestion or guess, or generate the next token if the big model thinks the small model did it wrongly. But this can accelerate generation a lot because small model can actually guess a lot of the tokens that big model would generate. And this paper explains that we shouldn't even waste computation trying to teach the small model to predict very difficult tokens that it cannot predict. It doesn't have capacity to predict. We should just focus on teaching it to predict as many of the easy tokens and as accurately as possible. So there are different ways of speculative decoding, but one way is for the fast draft model. It's called draft model because it's generating draft that the big model will accept or reject. And it can generate 5 to 10 tokens, and then the big model will look at the entire sequence of 5 to 10 tokens and decide to accept it or not in a single parallel step. But it can also accept part of the sequence, and so it can accept first 4 tokens, and then if the 5th token is not good, then it will discard 5th token and everything after. So it can accept the entire sequence or the first part of the sequence. And then the big model will generate that exact token that was not good by the small model, that was difficult to generate. And then this process can repeat, generate next 5 to 10 tokens, for example, and repeat. So the speedup comes at accepting multiple tokens at the cost of one forward pass of the big model. So instead of generating one token with one forward pass, we generate multiple. But this all depends on the acceptance rate. How many of those tokens are accepted? To achieve high acceptance rate, the small model must be aligned with the big model. It must think like the big model. And this is usually done by distillation. So you generate text with the big model and then train the small model to generate same text. And it will generate same text, although it's smaller, so it will not be as smart. It will not be able to fully generate the same text. But it will be very similar. But this paper finds a flaw in this approach because there is misaligned goal. The small model is trying to minimize the difference, the scale divergence of probabilities. So the small model is trying to make probability distribution over tokens of the small model same as probability distribution over tokens for the big model. But that's not the same goal as in speculative decoding, where the goal is to maximize acceptance rate. Or in simpler words, we shouldn't be teaching the small model to perfectly imitate big model because it doesn't have brain capacity or brain power to do that. We should instead focus on it teaching to just solve the simple tokens that it can solve as good as possible and not waste compute and effort into trying to solve tokens that it cannot solve. So the key insight of this paper, AdaSPEC, is don't waste the draft model's time on tokens it's bound to fail. Instead, let it master the ones it can actually learn. Join my school to become AI researcher, link below. This is how we do this. So, we have two small models. The first small model, it's gonna be called the reference model. It's just what I described. It's just learned thought with knowledge distillation to imitate the big model. Just what I described, the flawed design. But we will use it to train a better small model. So first we need to see which tokens are too difficult for this small model to learn. We don't want to waste time on those tokens that cannot be learned. Which tokens are too easy? Those can be learned very quickly by the small model as well. And which tokens are kind of medium, so they can be learned by the small model, but it needs a lot of time. So we will not waste time on learning these impossible tokens. We will invest more time in learning these medium difficulty tokens for the small model so it knows them better. So this is how we will find which token is in which group. So we can take the loss. It's like loss. In this case, we will calculate as probability divergence between this reference small model and the big model. So what I mean is, if for this token, a big model has one probability, but the small model has very different probability, that is the difficult token for the small reference model to understand, or for the small model to learn. So their probabilities are very divergent, it's difficult, it doesn't know what to do. So that's a difficult model. So then the loss there would be high. The loss for the small model would be high, because their probabilities are very different. So we want the probabilities to be as close as possible, but if the token is difficult, they will be different, so the loss will be high. I don't want to confuse you with this formula. So here, both reference and the draft, both are the small model. But let's ignore this formula. Let's just think about this reference. This is the small model that was just trained as best as possible with the classic knowledge distillation to imitate the big model. So this is what I was explaining. And we will use that model to find which tokens are difficult. So if the probability here is different than the probability of the big model, it doesn't know what to do with this token. Loss is high here. If the probability of this reference model is same as the probability of for that token for the big model in that sentence while generating, then it can mean two things. It can mean that this token is very easy, so this reference model learned it pretty early in the training, or this token is medium, so it learned it, but it needed more time. So we don't actually know which one of these two it is. We just know that it learned this token, but how difficult the token is between these two, we're not sure. And to distinguish between these two, we're gonna train the third model, and that's gonna be our draft. And so this draft is the actual model we are now gonna train to be better than this reference model that used classic type of training with just classic knowledge distillation. And this is how we will do it. We will just train this draft model a little bit, just a little bit. And then we will use a method of comparing its loss with a bit of training of the small model, a lot of training of the small model, and the big model. We're gonna compare all three models to see which tokens are easy, medium, or difficult. So imagine this. If a token is very easy to predict, then even with a bit of training, it will learn it well. So with a bit of training, it will have similar probability with the big model. And this reference will also have similar probability to the big model. So both of the losses will be low if the token is very easy. So then the difference between losses will be small, because this is a low loss. The difference is very small, delta L. Now imagine that the token is too difficult. Then both of the losses will be high because the small model cannot learn it. So the reference model, even if it's trained a lot longer, it still doesn't learn it. And this one especially doesn't learn it because it's trained for a short period of time. Both of them are small models. So high loss versus minus high loss will still have a bit of difference in the loss. So the difference in the loss will be minimal because both of them have high loss, and when you subtract them, you get very small difference. So that happens for difficult tokens. But the third situation, where the token is medium difficulty, where this reference model that had more training learned it, and this draft model with a bit of training didn't learn it, then this will have high loss, this will have low loss in comparison with the big model. So then this difference will be high, the difference of the losses will be high. So this is the only situation where we have high difference of the losses. And this is how we pick these tokens that are neither too difficult, so they can't be learned, or too easy, so they're mastered. So we will pick these medium tokens and just train on them. Generate text and that contains them and just train on them. And then we will just continue training this draft model on these medium tokens. So we will not train it or too difficult or too easy already mastered. All of the effort goes into training on these medium tokens that I just explained how we select them. You can rewatch if you didn't understand. Here it explains what I just explained, so you can read, but it just says again that high loss difference means the small model with a lot of training learned it. So, and the draft with a bit of training didn't learn it. So we need to focus on those medium difficulty tokens. And just to clarify, so the reference model is better at those medium tokens, but it's not as good as it can be. So it's still suboptimal. So our draft model that we are now training specifically for those tokens will be better than the reference model with the same amount of compute and effort. They found that the larger the model gap, size gap between the big and the small model, the better their method works. So that's gonna be it for this video. Join my school below the video to become AI researcher. It's for free for a short period of time. I'm gonna make it paid. You have all of these courses and we're all learning together. So see you in the next video.